Yeah, please. Sorry, not really. Yeah, no. Yeah, anybody, please. Yeah. It's that's the biggest story we have of the health building today. Yes, so it gives me great pleasure to introduce Revantha Ramanayake, who will talk to us about cut restrictions, simplifying cut formulas that are not eliminable. Please go ahead. Thank you.
Okay. Well, first of all, let me thank the organizers for putting together a wonderful workshop. It's a great pleasure to be here. In fact, I'm going to start on a note of regret because coming just 2 hours or 2.5 hours from here, all the local work sort of attracts you in, and so I only come for today. And already I see already that's a reason for a little bit of regret. It's wonderful to see. This wonderful event, but also many familiar faces, friends, research colleagues. So, thank you. Right.
Need to click on with the button
on one of these ways. Right?
But maybe I think you need to click with the mouse on the
side
somewhere, and then.
I understand this, and then yeah. All right. So, cut restriction. Let me. Put it in the perspective of the talk, for example, first talk that we heard today about a very nice talk about giving cut-free proof systems for logics and theories. Also, we know Andrea has done some very nice things on understanding proof systems for various logics, and a lot of work exists because most logics do not have a cut-free. Nice cut-free proof system. We want to, when we want to study a logic proof theoretically, which means we want to have a nice proof theoretic handle on a logic, but unfortunately, most logics don't play game with that. We don't have a cut-free proof system. And certainly from structural proof theory, which we also heard in the first talk, the idea is to say, okay, Gensen gave us a way of reducing or eliminating cuts, and how can we extend that to all the logics that we want to study? And there are lots of logics. And this talk is about considering the situation instead of when the cuts are not eliminable, instead of eliminating them, instead of moving to a new system where we can eliminate them, we want to stay inside Gensen's familiar sequence calculus system, and accept cuts, but restrict the cuts that need to appear. Okay, so rather than elimination of cuts in some more complex system, we want to restrict the cuts. This is what we call cut restriction. And then we could say, how bad are the cuts that we have to include, right? So a boundary case could be analogy cut restriction, where you restrict the cuts, but there are still some formulas of whatever you want to prove. And you could think of more complex cuts as well, right? But you do want to say that there is some connection between the cuts that you include and, for example, the formula that you want to prove. And that's really the tone of this talk, and I'm going to talk about various flavors of this type of restriction and how it fits in with other structural proof theory. This is joint work with Agatha Cevatoni from TU and Timo Lang from UCL. And this is work that has been going over the last 5 years or so. Right, so this idea that some logics don't have a cut-free proof system came about, a couple of decades after Gensen gave these nice cut-free proof systems to study classical logic, intuitionistic logic, and so on. So I think it was in maybe the mid-1950s for S5, the model logic S5, already there was no cut-free sequence calculus. And then you could say that since the 1950s, since the 1960s, one of the responses, and I would say the dominant response, if you look now back at this literature, was to extend the proof systems, say the sequence calculus, with extra structure to be able to prove cut elimination. So already you can see in a paper by Mintz in Russian from the mid-1960s, there is essentially a hypersequent calculus there to handle S5. And so therefore, here you might just by looking at the notation, you might recognize some of the proof systems. Several of these we have actually talked about already today. And you could also put labeled proof systems here. I guess I did that as well, of course, yes. So we have indeed talked about some of these systems here. And what we want to do, what I want to talk about in this talk is instead or as an alternative, right? So this program has been vastly successful. We've captured lots of logics with cut-free systems. We proved things about logics using these systems. So, sort of complementing that, what I want to do is I want to talk about whether we could have stayed with the sequent calculus but restricted the cuts. And the first thing you should ask yourself, of course, is it reasonable? Maybe is it possible to do this? And the answer is yes. So, first of all, you can see isolated results in the literature from the late 70s. Takano, in particular, I should mention, from the 70s until like now, has kept writing nice papers where he shows how to restrict the cut formulas. And there are more examples here, isolated examples of various logics, often modal logics. And what we did around 2019, 2021 as a proof of concept was we actually got this cut restriction result for substructural, intermediate, and modal logics. So that sounds already like lots of logic. I call it the proof of concept because we did it in this way. We started with systems that were cut-free, and in this case, cut-free hypersequence systems. And I'll explain what those are. And we went from there back to the sequent calculus, and we introduced cuts. So the point is that we started from a nice place because there were no strange formulas here. And we just had to remove the hypersequence structure, and we traded that for adding some cuts. So it is possible for lots of logics. And that already sets out the program, right? That we want to, can we use these restricted calculi for example, proving results like interpolation or complexity, for automated theorem proving. And the carrot here is that now you have just one system, and it's just the cuts that is controlling, the form and the type of cuts that is controlling the different logic that you get. So you're just one parameter. And we have had some results in this regard by various authors. And that's point one. A second point of this program, if I have to put 2 points for it, is to say, can we directly, you give me a proof with cuts, what is the algorithm in analogy with cut elimination for restricting these cuts? Right? And already in our heads, we might think we know that cut elimination has some nice computational interpretations, for example. Could those interpretations be extended now to this weaker, but still hopefully useful notion of cut restriction? So that's why I talk about reductive arguments. We have extending, Kahana has really set the ball rolling here with his work for S5 from 92. And we've shown in several isolated cases how to develop an extended cut elimination or a cut restriction algorithm. And our hope is that these give us the ingredients ultimately to even give a general cut restriction algorithm. Okay. Don't hesitate to stop and ask a question if you need help. All right, so I want to give you because I am aware that there's a lot of knowledge here about these various proof systems, right? I want to already give you an idea of how this cut restriction works, right? So I'm going to start from a cut-free system. So I want to give you the proof of concept that I talked about. So let's say someone gives me a cut-free hypersequent calculus. Now, if you don't know what a hypersequent calculus is, but you do know what a sequent calculus is, sequent calculus is a sequent, right? The proof is built from sequence. But imagine instead of having a sequent, the proof is built from finite sets of sequence. And so this is a finite set of sequence. It's actually two sequence, and this bar is like the separator. So you can see that now the rules in this case have a sequent here and a sequent here, but it gives you a set with two elements in this particular case. So already for the hypersequent calculus, it's known that you can get cut-free systems, cut-free hypersequence calculation for infinitely many logics, substructural logics, intermediate logics, even modal logics. And let's just take this as an example, right? This could be a substructural logic, it could be a intermediate logic, right? This rule applies in both cases. And this is what we do. We don't like this bar here, right? Because we want to stay in the sequence system. And we observe, you can imagine this like a gadget or some sort of transformation, which takes this, the stuff that's in blue here, gamma 1, delta 1, pi 1. We do some reasoning, and we get gamma 1, delta 2, pi 1. So we get the conclusion of some portion of the conclusion. We've removed this hypersequence bar, but it came at a cost. We've had to add some other information. So we've traded the hypersequence structure by adding some other information. So that means that we can run the proof, but of course that information that we added is going to stay till the very end. So we didn't prove F anymore, we proved something implies F. You could imagine that in the same way for every component here, I can get a proof. But each of those proofs will have some additional information. But things are not very bad here, because remember I said that this is a cut-free proof, which means that all these, these sets or these multi-sets, however you want them, these are, consist of subformulas of F. So these gammas and deltas and pi's, they're all friendly sets of formulas. And if you look at the additional information that we have added, it's some propositional combination, a simple combination, in fact, right? Bounded, right? It's in this case very bounded of depth 2 of friendly formulas. So from a proof of F, we have said we can prove F from implications of friendly formulas. In fact, we can get rid of this by doing a cut. And I mean, the answer here is, you can see this is delta 2 implies delta 1. If you did the same game on this component, you would get delta 1 implies delta 2. And it's not shown here, but the corresponding axiom for this is prelinearity. And in intuitionistic context here, which is P implies Q or Q implies P. So what happens is that you can actually remove this by a cut. So you do have to put a cut into the proof, but the cut is now on subformulas of F. Right. And this really does extend to all the infinitely many hypersequence calculi that capture these infinitely many logics. Right, so we already have recipe. Now, what about a reductive algorithm? That's the thing that I want to talk about. Where really what I really want is, you give me a proof, and I want to say that I know how to permute the cuts upwards and eliminate these, or simplify the cuts when I cannot eliminate them. So what's the interest in such a thing, right? First of all, cut elimination is extremely robust. You give me a proof system. I don't know whether cut elimination holds, but at least I know what to try. I will use Gensen's systems, Gensen's argument. And if it doesn't try, well, I still probably could try a few tricks. Maybe I fail, but it's clear this argument, you could say it's a robust algorithm. It works in many cases with many adaptations. What I'd like to say is that, and it's logic independent, it's semantics independent, Gensen's argument. Right? The same thing works in a substructural logic or intermediate logic, even though the semantics are widely different, or in classical logic. So I would like to say that we can have a cut restriction algorithm which is uniform over many logics. So how can we adapt the cut elimination algorithm to restrict what you can't eliminate, or simplify what you can't eliminate, which is the title of this talk. I want to go more, then we could look at cut elimination, which we've seen since mid-1930s, right? And has been a sort of landmark result, right? And used by Gensen in arithmetic, used in many places, studied in its own right, used in areas outside logic even, right? Through its computational interpretation, for example. But maybe that's just the tip of the iceberg. And maybe cut restriction actually is though cut elimination works for classical logic, maybe cut restriction is actually the general phenomenon that we need to be trying to interpret. And that all emphasizes the need for a reductive algorithm, right? Because that's where a lot of the usage of cut elimination comes, and its interpretations come from the you could say the constructive algorithm. Right. So a special case. Okay, so since we don't see how to do cut restriction in general, okay, let's be a little bit modest and say analytic cut restriction is a cut formula. You allow cuts, but they are subformulas of the cut rule. And then the first result that we know of a reductive syntactic algorithm for that is Takano from 1992, where he considered S5. Does anyone know this algorithm? Does anyone know the result that S5 has analytic characteristic? So I always, for many years, I always thought, how does this argument go without looking it up? I assume that you try to eliminate the cuts, and when you get stuck, you can figure out how to put a cut formula that is smaller. It sounds a decent idea, right? If you know cut elimination well enough, yeah, you lift it up. I cannot eliminate it, but then I must be able to combine it in some way to make it smaller. In fact, the argument does not go like that. It's a very complicated, and there's a little bit, it's hard to follow, right? So it's a complicated algorithm, which ultimately does show that for S5, you only need analytic cuts. Inspired by that, inspired by the proof of concept, we identified some sufficient conditions for analytic cut restriction. But even this is not broad enough, for the ambition that we want. We want to extend to lots more logics. And sometimes we know that it can be restricted to analytic cuts by semantic argument, but we don't have the syntactic argument. So once again, our hope is that we can uncover new transformations and then see how to put all these ingredients in to say this is the general cut restriction algorithm. Right? That's what we're chasing. So to give an idea of what such an general cut restriction argument might look like, let's go back again to Gensen and let me do a retelling of what cut elimination is. Right. So if you have not seen cut elimination before, let me try and explain it at a high level. So we have a proof system. We have a rule like modus ponens, a generalization of modus ponens, right? It's emphasizing something like transitivity of reasoning. So you could read this as X implies A and Y implies C. Well, then we can conclude that X and Y implies C. That's a couple. And it's let's say it's coming in some proof. Now Gensen is saying, I know how to eliminate this cut. What does Gensen do? Gensen says, all right, look at the formula that we want to cut or to remove. It's an A in this case. See where this A comes from. Okay, we have a tree. The proof is a tree now. So you can trace up the origin of this formula. Where was this formula born? And you can permute the rules up one or both branches. And in that sense, you can clearly see that the cut is becoming smaller, right? It's reaching the leaves of a finite tree. At some point, you cannot permute any further because the cut formula actually was born just above it. Look at this A has become A or B. So I cannot lift above this. I can't lift in the other branch either because A or B has again been its principle. It's been created there. Then Gensen has built enough into his proof system, which means that the formulas get created in a very orderly manner. And that allows him to say, oh, right, if A or B was created here, it must have been created from an A or from a B. If A or B was created on the left-hand side, then there must be an A here and a B here. Well, we can combine the premises and do a cut instead of A or B on something strictly smaller. Once again, the cut has got smaller. Okay, so that's the idea of cut elimination. You lift it up until you see where it's created, and then do some cut on something smaller. Okay, and the meaning of smaller in both of these cases changes across logics, but the idea stays the same. And now I would love to give a talk like this, where the starting object is a general cut, and the final object is a restricted cut. We won't get that today, but we'll get a specific version of this, right? But it also maybe indicates the type of ingredients that we have to put in. So I'm going to talk about a specific case here, which is tense logic. If you haven't seen tense logic, that's okay because I have the definition here. You can read this just simply syntactically as some sort of rewriting rules, for example, and I think a lot of the points still come true. So okay, it's the modal logic K. So it's classical logic, proposition and classical logic. And we have a modal operator, a normal modal operator for K, a box. And now we have tense logic, which is also a black box. So you have a white box and a black box. You have a necessitation rule for it. The white box and the black box are connected, right? So the white box is like saying forward in time and the black box is like saying backwards in time, right? So there must be axioms that relate the two, and this is like saying if A holds here, well, in every future world, there exists a past world where A holds. That's the converse axioms that tie the two modalities together. All right, so that's cryptic semantics. A sequent calculus was proposed by Nishimura in 1980, and it looks like this. If you know the K rule, you know what the K rule says. It says from gamma A, you can get box gamma box A. That's what the usual K rule is. But now because we want KT, in addition, there is a delta in the conclusion, which becomes bigger in the premise. So you can remember this rule as the K rule plus the other modality becomes bigger in the reverse direction. Same thing with the black box. So gamma A becomes box gamma black box A because the white box and black box behave in a complementary fashion. But this delta has become bigger. So you can already see that this rule does not have the subformula property, right? Because you could have a bigger formula in the premise than the conclusion, which means that if I want to find a proof of a certain formula in the sequent calculus, I'm forced to look at bigger and bigger formulas, right? And from here, it's not clear how much bigger I have to look at. And Nishimura also observed already that in 1980 that cut elimination does not hold. How do you prove something like that? Well, you find a sequent that you know should be provable, and this one should be provable. It's simply the converse axiom. And you give a proof with cut, and you can do some case analysis and say, hey, there is no other proof except the one that uses cut, right? And if these formulas are very simple, you can just look at all the options. Right. So cut elimination does not hold, so we are going to have cuts. The question is, how bad should these cuts be? We can see that there are only 3 rules that are going to do bad things, cause non-analyticity, or cause strange formulas to come into the proof. One is the white box and the black box for the reason I mentioned, and of course there's a cut rule around as well, which can introduce something strange. So let's measure things to try to see how we can remove them. So if you give me any of these rules, right? I'm going to say that the grade of non-analyticity, or the degree of how bad it is you take the largest formula witnessing non-analyticity and the size of the formula. So in the case of the cut rule, A is already witnessed. Here you must consider the formulas in black box delta and take the largest formula. That's the grade of non-analyticity. What we're going to do is, you give me one of these rules. Imagine that everything else is nice. This is the first time something non-analytic happens. We're going to transform this proof so the grade decreases, just like what you do with cut elimination. So we're going to show something like this. Let alpha be a proof. Let's say it ends in a non-analytic rule with positive grade. Well, we're going to it's not just existence. We're going to actually create a proof of the same sequence where the non-analytic rules have smaller grade. Right, let me give a little bit of flavor of the type of argument to see how it extends what we know as cut elimination. So here is a proof, a schema of a proof. Let's say that this place is the place that non-analyticity first shows itself, right, going down from the leaves. And let's say that this stuff in red is, the witnesses of non-analyticity. So the red delta here. Well, we can see what happens. We have a proof in front of us. We can imagine that these deltas will be will at some point decompose into smaller formulas. So here's the box B, right? It's become smaller, right? Of course, you want to check that other things would not have happened, but you can argue this, right? I just want to give you a very high level view here. So let's call these are the bad formulas. And this is where the bad formula gets decomposed. And in blue, we're going to call it critical formulas, are the context of the bad formula. Bad formula gets introduced or decomposed, depending how you want to see it. And the sigma and the box file are the left and the right critical formulas, the context of this bad formula. So there are analytic formulas that occur in the context of non-analytic formulas. I know that they're analytic, by the way, because I chose the topmost bad one. So everything else is good. Okay, and here's the first thing. I'm going to give it to you as an algorithm. You collect all these bad formulas, the critical formulas, left-right critical formulas, and this is the sequence you want to reach. You start doing cuts on all of them, or you introduce these formulas as cuts, right? So let's say C1 to Cn is the set of critical formulas where you do a cut on C1, which means you introduce a C1 on the left and the right. It's actually a case split, right? A formal case split. Then, so this assumes that C1 holds, this one assumes that the negation of C1 holds, right? Then here again, you assume that in this branch, C2 holds or its negation holds. So what do you get? You get a binary tree with this many leaves. If you can prove each of these leaves in a nice way, I mean, without doing, hugely non-analytic things, then you have the desired proof that you wanted. So I'm going to convince you that that we can prove all of these leaves. Each leaf has this form, right? It has the stuff that we wanted, plus the C1 and C2 sort of a partition of all the critical formulas, right? Because critical formula goes on the left, on the right. So if you take any leaf, there's some stuff on the left, some on the right. So the left stuff we call C1 and the right stuff we call C2. Let's say that this pair is aligned if the pair extends something that you already had in the proof. Remember, these were the critical left formulas, these were the critical right formulas. So if you have C1 which extends a critical left set and C2 which extends the critical right set, I mentioned this point, then it's easy to prove, right? Because you already have a proof of this by looking into what was given as input. And in this particularly nice case, the sigma I can be extended to C1. The box phi I, which is the right critical formulas, can be extended to this one. And there you go, you've proved your leaf. So the interesting case is the other one, where it's what we call non-aligned, which means that, what is it saying? Some left stuff has occurred on the right, and some right stuff some right stuff has occurred on the left, right? How do we handle this case, right? All right. So the short answer is this. Okay, let me motivate it like this. Now we are in this case here, where we have some partition C1, C2, one of the leaves. And by the case split, we know that some left stuff has appeared on the right, or some right stuff has appeared on the left. Now in the proofs we have so let's say the sigma I. We should have seen it on the left, but it has appeared on the right. Which means that we have a proof where sigma I appears on the left, in the original proof, and some sigma i's appear on the right. But that's exactly what you need to get an axiom. Right? So if we know that I mean, it's like saying you're driving and someone is driving. If someone is driving on the other side of the road, you'll surely pass them, right? In a very restricted setting. But if you're going the same way, you may never pass them. One road, and someone says, oh, someone is driving on the wrong side, sort of ahead of you in something. So of course you're going to pass them. And that passing is like the axiom that's happening. Yeah. So we just need to find this place and sort of say something about where it happens. And that's what this picture shows. Right? This is the leaf that we want to prove. I do things to make it meet the proof that we had before or something close enough to that proof. And here's the point. For example, this is the stuff. This is the stuff that is on going the wrong way, and this is the original one, and this is when they meet. Or maybe this is the stuff going the wrong way, the car going the wrong way, and this is the original cars, and this is when they meet. Right? I have to go into more detail of that, but I think it's enough already to just get an idea of what this picture means. Our task is not done because I need to also make sure that whatever I have done here preserves this, this analyticity property is actually more delicate than it looks like, right? Because remember, I've removed one formula and put other formulas in. I've replaced one formula with other formulas. But analyticity says that whatever you see in the premises, you can see in the conclusion. And if you remove a formula, that formula that you remove might have been witnessing this property for multiple formulas, right? So when you remove that formula, it might have been like the witness to say, yeah, that guy is a sub formula of me, or I'm a, however you want to say. Now if you remove it, now that witness is gone. So you need to convince yourself that whatever you put back is good enough, right? And that's what this argument is. You need to show that this adapted proof that you put in here to reach the two cars meeting, you need to show that itself is analytic. And so you identify the two sources of that non-analyticity. And well, you have to be a little bit careful, but you can show that you have put enough into the system really to show that the proof that you get is good, right? So for example, let me just consider one case. Let's say you have this adapted proof. This is an adaptation of the original proof of the input. Let's say that you had an analytic cut rule, because there could have been cuts here, right? Analytic cuts here on some formula D. And let's say it's no longer analytic here. Well, that means that we must have removed the D or something larger. So you can argue that therefore the non-analyticity in such a case is actually a small one, not a large one. Right? That's the type of argumentation you do. But yeah, I can come back to these pictures if you wish at the end. But for now, I think that's enough of the high level point. Right. So you proceed like that, and you can see it's more elaborate. At least the version I've given you here is more elaborate than what Gensen is doing to eliminate the cuts. Is it forced? I don't know. Right. It's also not as nice as what Gensen is doing because I introduced a lot of cuts, so I sort of added some arbitrariness to the proof. Is it bad? I don't know. But at least I'm restricting my cuts, and it's in fact easier than say the argument style that Takano uses, right? So there's some improvement here, but it's not clear whether we can do better or not, or even how we should measure better, right? Okay, let me put the cut restriction argument, justifying that to a side, and we just observe some observations here. Like here's a potential interpretation of this algorithm. So since we were doing modal logic, we know cryptic semantics, right? And we know that you can also talk about a proof as trying to find a countermodal, right, or falsification, right? And what you do is you take the proof and you say assume everything on the left is true. You want to show that something on the right is false, right? Because that's an implication, right? So the left is true, the right is false. And in countermodal construction, that's what you do. And if you see a box on the right, you try to find a place that falsifies that box. And our algorithm we saw was introducing these analytic cuts, right? You just look at all these critical formulas and you introduce them as a case split. So you could interpret this as saying when you can't do any obvious things like invertible rules, right? Then do a case split on all these critical formulas and pursue one of these to see if you can find a countermodel. In fact, I guess you need to find a countermodel on both of those. But yeah, the point is do a case split on analytic formulas at your current world in the cryptic semantics. Right. The final thing I want to bring up is I want to go a little bit ahead and talk about this general cut restriction algorithm, give you an idea of what I have in mind, what I would like. So here's the intermediate logic, Gödel logic, which is intuitionistic logic plus some axiom, plus this particular axiom. You gave me a proof of F in this system. We want a cut restricted proof, right? Because no one said cut is not eliminable here, in fact, right? But I want to restrict the cuts. Which means that from pi, I want to obtain a proof of pi prime. Okay, so here's what I've done. This is a proof in LG. I can always make a proof in LG into a proof in intuitionistic logic by just putting down the axioms that I've used. So these are the axioms I've used. The problem is I don't know that these axioms are nice instantiations. Are they related to F? Right? Will they be just random formulas or ones that I cannot compute? So here's an argument that works in the basic case. Let's suppose I was lucky and the proof pi you gave me, when I asked you to give me a version in intuitionistic logic, let's say it only had one instance of the axiom. A implies B or B implies A. Now I still don't know the identity of A and B. However, if I, for example, this rule is invertible, if I try and imagine, try to argue on essentially a case split on what this proof looks like, you will find some place where this was introduced and where this was introduced, right? And where this got broken up like this. And then, this might sort of ring a bell with what we saw with the hypersequent argument. You can see that the gamma and the pi, if you do this carefully, actually belong to F. Because you trace the bad formula until they got opened up the first time. And these are, another way of saying it, these are the critical formulas in the tensed logic case. The ones that we needed to use to construct the proof. Right? So you break up the bad formula, you look at the stuff that's around you. And I'm observing that these critical formulas are subformulas of F. And then, well, in this simple case, you can actually transform. What do? You say, hey, the A and the A here can do a cut on something smaller. So you can reduce the proof. The B and the B can cut, which means you get this picture, you come down here. Once again, you do have to do a cut, but you're doing cuts on gammas, on stuff that is friendly. Right? Or some very sort of constant propositional formula of stuff that is friendly. So we need to extend this argument, you would think, to general ones. You think bet that it should work, right? But things do become a bit messy when there is nesting in one way and in the other way, right? So we don't have that. All right. So that brings me to a conclusion. And here, what we have here is a picture of now the world as we want to see it. So no cuts are required for some logics. Sometimes you need analytic rules. Sometimes you need to violate even analyticity. So Takano says that something on K45, you need essentially cuts, but not just on subformula, but maybe boxes of subformula. But you don't need it on boxes of boxes, for example, right? Something on those lines. So that's a mild violation. And you notice that that's good enough to get, for example, complexity optimal bounds, right? But you can go much worse. You can talk about sets of subformulas, right? Even that's good enough. Well, no. If you have sets of subformulas, immediately you're going to get some sort of you could get an exponential blow up in your complexity because you need to consider all the sets, right? And that's where exponential blow up comes. Substructural logics, you can only say you can identify the form of the cut as say products of subformulas, but that's not good enough, say, to argue about complexity. Because you can't say anything about that product, right? It's arbitrary products in a substructural logic. And then this is the case where arbitrary cuts are required. And we would like this red to come and extend to be able to do restriction arguments for all of these up to there. So that's extending the reductive argument. Of course, once you have these cut restricted systems, question is what can you prove something about it? Can you prove interpolation, for example, with cut restricted systems? There are some results, for example, Sano and Ono, where they use analytic proof systems, analytic cuts or something even slightly more and get interpolation. It would be enticing to see, can we uniformly now, we have a nice representation of all of these proof systems just by changing the cut formula. Can we get general interpolation arguments, right, or sufficient conditions for them? Complexity issues I mentioned here. Computational interpretations of cut restriction. What does it mean to say that the cut has to be, sort of a Curry-Howard type of interpretation? Modulo automated theorem provers. You build one system, you build your heuristics, and the only parameter is the different types of cuts. So we, with a master's student and another collaborator, we built some proof systems, but we didn't build any heuristics, so we can't say much about how they are doing. But at least in theory, yes, this can be brought about. And then you could always think about formalizing these things just to get a bit of a hang on automating this reduction procedure. Thank you.
questions or comments? Yes.
Yes, I mean, you mentioned, I mean, I received a calculator and you showed us as an exemplification, the kind of translation backwards for these missing parts. So did you try also other extension of VSA calculator?
No, we have not.
Only have received.
Yes.
Fine now.
Yes, please.
I was wondering if you can say a bit more, or if anyone has done any research that you know about the not the last point, but the one before. So the whether you can do like proof search with analytic cuts.
Wait, you mean which one? This one?
The one before the last one. Yeah. So how can you do proof search with analytic cuts?
Okay, so well, the most naive thing to do, of course, is that when you can't do anything that is safe, which is what you would normally do first, then you could say I introduce my cuts. Okay. So in fact, if you look at how they do this automated theorem proving, they actually build quite surprising and actually very neat heuristics on top of that, right? Sometimes they're heuristics, sometimes they're other optimizations. So, for example, do you need to put all cuts in? Well, maybe, I mean, if you can find a propositional variable that is not in common, probably you don't have to put it in, right? That's the type of optimization that I can imagine you could add. Yeah, I'll be curious to know how good it can be. Yeah.
Other questions or comments? I have a quick question. If you look at the normalized proofs in the hypersequent cut-free system versus, is there a notion like normalized, is it still unique normal proofs for the cut restriction and other proofs comparable in size? Or does cut restriction give you better or worse properties?
Yeah, so that's something that we wanted to study, right? Which is the size of cut restricted proof with respect to the extended element, like for example, hypersequent. That's the proof. That's the question you mean, right?
Yes.
We looked into this a little bit. I think actually, yeah, I can't say I recall what we. For sure, we didn't get that. The nice thing would have been if our cut restricted proofs were smaller, right? For example, that would obviously be the thing. So obviously, that's what we try to do.
Even if they're comparable, it would still be.
Yeah, exactly. So that's the next. That's probably where we think it is. It's not. I don't think it's better actually. I mean, in many cases, it's hard to go. You cannot go an exponential down anyhow, right? Which you sort of for complexity considerations. So it could well be comparable. Even there, I'll have to dig up what we wrote. There was even there. It's not as simple as that. It would be easy to say it's comparable, but I think we looked at some sequences of proofs where that's where you want to prove the thing, right? That where R1 might even be doing worse, but I can't be sure now of this. So I can get back to you.
Thank you. Other questions or comments? No, let's thank the speaker again. Thank you, Vicky. We have to lunch very quickly because I like longer. You need to be back here soon. So
This should be your